Okay, hi, welcome to another session of the Potter's Roundtable from Washington Street Studios in Bolivar, West Virginia. We're surrounded by Harpers Ferry National Historical Park. I'm Phil Bernberg, and today we're going to be continuing the discussion of Pottery Figurin, that is, some math calculations that you can use in relation for pottery.
Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
So now let's talk about, we mentioned that there are three sections or three areas that we can talk about: glazes, and we're going to be talking about those first, and then we'll get to firing and other things later. So the first thing is, let's talk about a recipe, a glaze recipe, where we're going to be replacing one ingredient with another, but the formulas are not quite the same. So in this case, I have a recipe that calls for petalite, and I want to replace it with spodumene. These are both, petalite and spodumene are both minerals, and they're used primarily because they contain the flux. This is lithium oxide. They contain the flux lithium. So they're used as a source of lithium. And they also contain some aluminum oxide and some silica. So this is lithium oxide, aluminum oxide, and silica. And petalite is a little less common than spodumene as a material, and it's also a little more expensive. And a lot of places it's not readily available, but there are a lot of recipes that were produced in the past that used petalite. So it's fairly common, if you have a recipe that you like, you might want to substitute. You have spodumene, which is a fairly common ingredient, so you might want to substitute spodumene for petalite. So how do you do it? Well, we're going to follow more or less the same approach that we did for some of the substitutions in the first part. So the first thing I want to do is I'm going to look in the recipe, and I'm going to take the number of grams of petalite in the recipe, and I'm going to divide that by the molecular weight of petalite to tell me how many moles, remember, how many molecules, how many furry little brown animals of petalite I need. And remember, for these molecular weights, you can look them up. But again, the molecular weight of the petalite would be the sum of the atomic weights of all these elements: 2 lithiums, all the oxygens, 2 aluminums, 8 silicons, all of them. It would be, you'd add those up. By the way, when a formula is written like this, everything in the formula after the number is multiplied by the number. So this is SiO2, so it's really 8 silicons and 16 oxygens in here. And you'd add up all of those to get the molecular weight, but you don't have to do it individually, you can just look them up. So now in this case, I'm going to want to use the same number of moles or units of spodumene as in petalite, because the lithium is the same in both of them, the aluminum oxide is the same, the only difference is the silica. So what this really means is, if I'm going to substitute spodumene for petalite, I can do that, but I'm also going to have to add some extra silica to make up for what would have been provided by the petalite. Okay? So I'm going to use the same number of moles. So the number of moles of petalite is going to be the same as the number of moles of spodumene. Moles of spodumene times the molecular weight of spodumene, and this is going to give me the weight in grams of spodumene that I need. But now I also need to add the silica. So this is where I take that same number of moles of spodumene, and I multiply it by 4, because for each mole of spodumene that I substitute, I'm lacking 4 silicas. So for each one of these, I need 4 more of those. Okay? Because I'm missing 4. Instead of getting 8, I'm only getting 4. So I multiply the number of moles times 4 times the molecular weight of silica, and that gives me the weight in grams of silica that I need to add. So when I'm substituting the spodumene for the petalite, I use this ratio to convert the weight of grams of spodumene, but then I also have to add some additional silica for make up for the missing silica. I had to adjust for that. Okay. Let's change topic a little bit here and talk about blending tests. Just some basics when you're doing blends. If you're doing test blends for glazes. There are different ways when you're, let's say you want to do a test blend for a glaze, like add an ingredient to a glaze, and there are different approaches for doing it. One of the first approaches, and probably the simplest, is what's called an additive line blend. This basically means a mixture of two materials. And if I'm using separate batches for each one, this is very simple. Let's say I have 100 grams of something, and I'm wanting to add a colorant or some other material to a glaze or a recipe that I already have. I have 100 grams, of, let's say, of the base glaze, and I'm going to add 5 grams of something to it. If I want to, and maybe this is a colorant, or it's one of the other ingredients that's in the glaze. If I want to know what the actual percentage is, if I want to calculate the actual weight percent, then I have to do it like this. It has to be 5 over 100 plus 5, which would give me 4.8%. So I'm adding 5 to it, but when I calculate the percent, it's the additive, or the material added, divided by the total. So the fact that I'm adding it to the 100, I'm getting actually a little less than 5%. And if I added 10 grams, then the formula would be 10 grams over 100 plus 10, which would be 9.1%. So it's deviating a little, because I have to add it to the total, okay? Now this would be, if I was making up individual batches, I might do this. I might take 100 grams and make up a batch with 5 grams added, and another batch with 10 grams added, another gram of 15 grams added. And each one of those would be a separate batch, and I would take samples, let's say, to testing. I'd take samples of each one of those. But there's another procedure, kind of a shorthand way of doing it, which is even simpler. And I only make up one batch, and it's only approximate, but it's a great screening technique. And some people call this the blender method, because basically I'll make an addition, mix it up, take a sample, make another addition to the same batch, mix it up, and take a sample. And typically you could do this in a blender, so you get really good mixing. So in this case, it's going to look a little different. I'm going to take 100 grams, and I'm going to add, let's say, 5 grams to it. And so at that point, the percentage would be 5 over 105, right? 100 plus 5. Now and I take a sample. And then after I take the sample from this batch, I make another addition to it. So I add another 5 grams to it. And now it's going to look like this. It's going to be, this is the symbol for approximately equal, a little wavy line. So now the composition is actually going to be this. And the reason why I say roughly, because I've taken out a sample. I've taken out a sample in here before I made it. So I've taken out a little bit of what I was added, and I've taken a little bit of what was of the basic. So I no longer have the exact. So I can't calculate the exact percentages because I don't know how much was used by my sample. But the nice thing about this is I only have to make up one batch, and it's close enough for first approximation. If you want to sort of see what the effect of a range of additions is, it's close enough to get an idea about what's getting approximately the right value. Then you could always go back and do it precisely and to get the exact percentage if that matters. But this is a quick way with one batch of checking a bunch of different levels. Now the way to get it precise, if you wanted to get it exactly, this is where you'd make up what's called a crossover line blend. This is one name for it, a crossover line blend. And in this case, you can sort of think of it graphically. This is, again, is a mixture of two materials. I can sort of think of it as if I make like a plot, like a graph. And this is a line that represents all the different possible combinations or mixtures of the two ingredients, A and B. So at one end, I have 100% of one ingredient, and at the other end, I have 100% of the other ingredient. And I have all these different mixtures in between. So like this point in the middle is 50% A, and 50% B. Or this point here is 75% B and 25% A. But the point is that the mixtures of the two always equal, the total is always equal to 100. So if I have, whatever I have of the amount of one material, the balance, 100 minus that, is what I have of the second one. So this way I've got all possible combinations I can represent by this line, for example. So I can have one here, for example, that's 99% A and 1% B. And the point is, the total is always 100%. So I'm actually using true percent here, whereas last time I was essentially using parts, because the total was not 100%. In this case, I've got a true total of 100%. Now, and so this would be a normal way of doing it. I would frankly, this is the same thing, this is the same basis as a glaze recipe, only instead of having just two materials totaling 100%, I have 3 or 4 or 5, but the total still is always based on 100%. Another way for test purposes, though, if you're doing blends, would be what's called a triaxial blend. This is another way of exploring compositions, triaxial blend. And basically what I do is, I can represent it sort of by a graph here, and I can say I've got 3 different materials, and this diagram is going to show me all the different possible combinations I can have of either 2 of the 3 or all 3 of the 3. And I can I'm just going to draw some lines on here to make it a little easier to follow this. Again, this is a graph. This is just a graph. So what this represents at this corner, this represents 100% of A. So this point right here means I've got 100% of A. This corner down here is 100% of B. And this corner over here is 100% of C. So along each one of the outside lines here, I've only got 2 ingredients. For instance, I've got A and B. This is basically a crossover line blend. This is 100% A. This is 50% right here. This is 50% A. And this is 50% B right here. This is a crossover line blend just between the points on this line, like here and here and here. Those are supposed to meet, are just all the possible combinations of B and C, and along this edge are all the possible combinations of A and C. Within the triangle, I've got all the possible combinations of all 3. Okay? So this point right here is 25% A, and it's 25% B, and it's 50% C. And I'll show you how you count that. So what I do is I start at, if I'm going to be A, this line right here represents no A, right? This is just B and C. So this is, if I count these divisions, this is 0, 25, 50, 75, 100 A. So this point going up to here, that's 25% A. If I go to B, this line here represents 0 B, and this is 100 B. So I go 0, 25, 50, 75, 100. So this is 25% B. C, I do the same thing, 0, 25, 50, 75, 100, so it's 50% C. So basically, but again, I'm looking at all the possible combinations, but in true percent, where the total is always equal to 100. Okay? Let's talk about, go back to modifying glaze, modifying recipes, but now I want to talk about actually, more than just a recipe. Suppose I have an old bucket of glaze that I've been using for a while, and I've decided that I want to add something to it. Maybe it's a scrap bucket, or maybe it's a bucket of glaze that I've used, and I don't know how much water I've got in there. I don't know how much solids I've got in there, but I've got a glaze and I want to do something with it. I'm getting bored with it, maybe. So the first thing I need to do if I've got this bucket of glaze is I need to determine how much water and how much solid powder I've got in this bucket of glaze. So the easy way to do that is to take a small sample of the liquid glaze and weigh it, and then dry it, let it sit around and dry it, or put it in an oven or something and dry it out, and then weigh the dried glaze. And then if I take the dried weight So now this is just the powder. If I take the dried weight and I divide it by the liquid weight, I'll get the percent, I'll get a decimal fraction. I'll get a decimal fraction like we talked about before, but basically it will give me the weight percent solids. Basically what I'm saying is here is how much of the total weight, by doing this division, how much of the total weight of the liquid glaze does the dried part represent? So now what I can do is I can take this and I can weigh the full amount of the liquid glaze that I have left. So I can weigh that right in the bucket, and then maybe if I have an empty bucket, weigh the bucket and subtract that. So I know the full amount of the liquid glaze. And if I multiply it by this, now I get the total amount of solids. It's as if I've removed the water and I know how much powder I have in the glaze. And I need to know that before I can make any additions. So now, I'm going to make an addition. So suppose I want to add a new ingredient to the glaze. So I'll take the total solids weight. That's the dry weight that I've got sitting in this bucket of liquid glaze, and I multiply it times the weight percent of the addition that I want to make. Like, let's say I want to add 5% of something, and that will tell me the weight of my addition. This is the same as if I was making up the recipe. I have the total amount of solids, I multiply it by the percent I want to add, and that gives me the weight I want to do, okay? Now, if I want to actually calculate what's the actual percentage I'm going to get when I make this addition, this is what it's going to look like. It's going to be the weight of the addition divided by the total solids weight plus the weight of the addition again. And that's going to give me the actual weight percent of the addition. Because again, if I'm adding 5%, let's say I add 5%, it's going to be a little less than 5% to calculate the true percentage. Maybe I don't care what the true percentage is. I just want to add 5% and see what I get, and that's fine. But if you want to know what the actual total percent is, this is the way you would calculate it, okay?
Thanks for watching this video. Please like, subscribe, and share it with your friends. And consider becoming a patron of our channel. Visit www.patreon.com and search for the Potter's Roundtable. Any amount you give will support the creation of a digital library of educational videos and podcasts to support artists, potters, and educators now and into the future. If you would like more information about our membership studio, classes, events, and multimedia productions at Washington Street Studios, visit our website at www.hfclay.com.
Now, suppose I want to add, that was a new ingredient that wasn't in the glaze. Suppose I want to add more of an ingredient that's already in the glaze, so that I know what the recipe is for the glaze, and I want to add more of it. So I'll do the same thing. I take the total solids weight, and I multiply it times the recipe percent, how much is in the recipe, and that tells me the weight of the ingredient, the total weight of the ingredient that I'm interested in. Because if I know the total weight of all the powder in the glaze, and I know the percent that the recipe said was in the glaze, this tells me now how much of that one particular ingredient I now have. And so if I want to find out, and if I make an addition, and I want to find out now what's the new percentage, this is what the formula would be. So this would be the weight of the existing ingredient, the weight of the ingredient, plus the weight of the addition, divided by the total solids weight, plus the weight of the addition, would give me the new weight percent of the ingredient. Because I already had some of this ingredient in the glaze, I'm just adding more of it, and this would be a way of calculating what the new percentage is. I knew what the percent was in the original recipe. This would tell me now the new percent after making this additional contribution to the glaze. Okay? Okay. Let's change the topic here a little bit, and let's go on to I want to mention the use of specific gravity with glazes. This is sometimes people refer to. What is specific gravity? Well, the definition of specific gravity is the weight of something compared to the weight of an equal volume of water. And this is used, people use specific gravity to determine, since if I have a liquid glaze and I measure the specific gravity of that glaze, it's in a sense, it's telling me the proportion of water and the solids that I have. So, and I can actually calculate, so if I take the weight of a small amount of glaze, small amount of liquid glaze, let's say a cup, and I divide that by the weight of the same amount of water, that will give me a number, like a ratio, and that is the specific gravity. Okay, that's the way you actually calculate specific gravity. So if I took a cup of the liquid glaze and I weighed it, and I took a cup of water, or whatever the same measurement, and weighed it, and divided this, I would get the specific gravity. It doesn't have any units because it's just a ratio. It's just telling me how much heavier, and because with a glaze, all the powdered material is basically going to be heavier than water. So the same quantity of glaze is always going to weigh more than the same quantity of water. Okay? And people use this, so I can use this, if I can measure the specific gravity of a glaze, then I can use this to tell roughly what the proportion is of the water and the solid material. If I make up the glaze one time and the consistency is perfect for, let's say, dipping or pouring, and I measure the specific gravity, that gives me a target to shoot for every time I make up that glaze to reproduce the same proportions of water and powder. So if I measure the specific gravity, and then I make up a new glaze, and measure a new batch of the glaze, and measure the specific gravity, if the specific gravity of the new glaze is less than the original, it means I have too much water, right? Because water is lighter weight. If the specific gravity of the new batch is greater than the original specific gravity, it means I have too much powder. So I can make adjustments one way or the other. I can remove some of the water or add some more powder if I have it. Okay? Okay. Let's talk about that. That's all I wanted to talk about with respect to glazes. Let's go on just to the next two areas briefly. I have a few things I'd like to mention. And one is for fired pottery. Well, one of the things that's a good technique to use is measuring the percent shrinkage of dried pottery or fired ceramics. And if you want to calculate the percent shrinkage, basically what you do is you measure. You make a certain, especially if you're making, let's say, a test. A good way to do this is, for instance, to make up a shrink bar. You make up a bar that's about 5 inches long, and you scribe a line in it, and you make 2 marks that are exactly 10 centimeters apart. And then you can fire these tests, and this is about 1 inch wide, and maybe a 1/4 inch thick. And so you make it so that the line is 10 centimeters long to start, and then let's say you allow the clay to dry, and then you measure it again, and you want to know what the percent shrinkage is. So the percent shrinkage would be the starting measurement minus the final measurement over the starting. So and the nice thing about these dimensions is it makes the calculations easy. So if I started and 10 centimeters is also equal to 100 millimeters, and the reason why this is also useful is because it's very easy to read a millimeter on a scale. You can measure it fairly precisely. You can usually even estimate to less than a millimeter. So if you start off, it's 100 millimeters, and then after it dries, let's say, it goes to 90 millimeters, you've lost 10 millimeters. So you've got 10 millimeters, starting minus 5, divided by 100 is 10% shrinkage. So by using the 10, it just makes the math a little easier instead of using, because it's all nice round numbers. Okay? Now suppose I want to, another version of this, suppose I want to make a part to fit. And so I want to know, I know what the final size that I want is, and the question is, if I know the shrinkage of the clay, what size do I have to make it to start so that it'll shrink to the size that I want? And the way, and you set up the formula a little differently. This is the desired size. Desired size, and I divide this by 100 minus the percent shrinkage equals the starting size. So if I want the part, if I want it to be a certain size, and I know the shrinkage, let's say the shrinkage is this is 100 minus shrinkage. Now I do this in terms of, this is where I use decimal fractions. So let's say the shrinkage is 10%. So this would be 0.9. If the shrinkage is 10%, the shrinkage would be 0.1. So this number here would be 0.9. So what I'm saying is that the desired size is 90% of what size? That's what, setting up the equation like this, it says the desired is 90% of what size? And if I divide this, I get the starting size. Because to divide this by 90, I'm going to get a little bigger number than this. And that's my starting size. So that's the way I can make, if I know what the shrinkage of the clay is, and I can measure it, I don't have to rely on a reference if it's available. I can measure it, and then I can go back and make parts that will shrink to a particular size. Another calculation with respect to fired clay would be determining the percent water absorption. This is where, for different purposes in pottery, you want to make sure that the clay gets dense beyond a certain point or that it doesn't absorb a certain lot of water. And so there's a standard method of doing this, and you measure the water absorption. So what you do is you take a small sample of the clay and you measure the dry weight of the clay, and then you soak that piece of clay or you boil it in water. I usually typically boil it for maybe 15 minutes, or I soak it in water overnight. The boiling just helps the water penetrate the clay. And then I'll take it out of the water and I'll quickly wipe off the surface, just very gently. I don't want to actually absorb water that's been absorbed take it out of the clay. I just want to get droplets off the surface, and I'll weigh it again. And then I set up this calculation. I take the wet weight and subtract from it the dry weight. So this is giving me the weight of water that's now been absorbed in the pot, and I divide it by the dry weight, and that gives me the percent water absorption. Because the dry weight, the wet weight, which assuming it's absorbed some water, minus the dry weight, gives me the weight, just the weight of water that's in the clay. Divide the weight of water by the weight of the clay, and I get the percent, what's called the percent water absorption. One final calculation to talk about with respect to kiln operation is you might want to think about, this is a very simple calculation, but I think it's a useful one. People are always talking about the efficiency of their kilns, and so this is a way to calculate, to get a number for the efficiency of your kiln. And what you really want to talk about when you talk about the efficiency of the kiln is not how much fuel you used or how long the firing went. What you really want to talk about is the amount of fuel divided by the total weight of the ceramics that you fired. Total weight. And so really what you want to get it down to is like the amount of fuel per unit, maybe per pound, let's say, of ceramics. And this gives you a number that you can compare. It doesn't matter what kind of kiln it is. It gives you a number that you can compare. So for instance, let's say you're comparing one kind of wood kiln to another. If you look at the amount of fuel you used per pound of fired work, that's a direct indication of efficiency. So for example, for electric kilns, you can use if you have an electric meter that you can read. What I've done for this in the past is when I'm not firing, it's kind of hard to separate with an electric meter all the things that are using electricity. So what I'll typically do is a couple of times I'll go take a reading on the electric meter, like maybe at the beginning of an hour and the end of an hour, and I'll take the difference, and that gives me the kilowatt hours that I've used when I'm just using my normal usage for the house. And then or for my studio. And then when I fire the kiln, I do the same thing. I'll take a reading, let's say, at the beginning of an hour and the end of an hour, and get the kilowatts, and I can subtract what I had before, which was kind of the background of the normal usage, and that gives me my kilowatt hours. And so I can basically and if I weigh the pots when I take them out of the kiln, I can have the total number of kilowatt hours that I used to fire that amount of pottery, or kilowatt hours per pound. Okay, I can do the same thing for wood. For wood, I can measure the amount of cords of wood that I have, and I can say, okay, I used a certain number of cords for a certain amount of pottery. If I wanted to, I might even be able to, if I knew the kind of wood, for example, I might be able to look it up and say, okay, well, oak wood, for example, gives me a certain number of BTUs, British thermal units per cord. So I can write it even in terms of BTUs per pound, which is really a heat unit, which is nice. And for gas, I can do the same thing. I can measure the amount of propane or natural gas that I use in cubic feet and have cubic feet per pound. Or again, I know how many BTUs are in a cubic foot of propane or a cubic foot of natural gas, so I can convert it. So I can end up with BTUs per pound of fired pottery from my kiln. And this is the best. This eliminates all the other possible effects, because that's ultimately what I care about. I don't care about the size of the kiln. What I ultimately care about is how much fuel did it cost me to fire this work. And if I use a number like that, then I can directly compare the results of my kiln or my firing with somebody else's in terms of really talk about efficiency. So that's about all we had finally for these mathematical calculations. Again, we hope that this has been useful. And we know, again, this was a lot of information in one time. We do have handouts available if you're interested for this. If you'd like to hear it again, you can listen to it on our podcast version of the presentation. Just search for the Potter's Roundtable on your favorite podcast platform. And if you enjoyed the presentation, please like it and subscribe to it on our channel and share it with your friends and other potters. This helps our videos get found on YouTube. If you didn't like it, tell us why. Maybe we can do better next time. Also, check out our website, www.hfclay.com. Well, we really want to thank our patrons for supporting our educational efforts. And if you'd like to help us, consider becoming a patron. Go to patreon.com and look for the Potter's Roundtable. We have 5 options, 5 different patronage levels that you could subscribe to. And we decided, instead of naming them the typical gold, silver, bronze, platinum, we decided to give them clay names. So the first level we have is what we're calling a clay patron, and that's for $1 a month. And in exchange, you get recognition on our patron appreciation page in all of our videos. The second level that we have, we're calling a bisque level, which is $5 a month. And again, you get the recognition, plus you get a Potter's Roundtable sticker that you can put on your laptop or wherever you like, or on your forehead. Looks like this. The third level that we have is called the earthenware level. That's $10 a month. You get all the previous benefits, plus you get a transcript of any available episode that we have every month, a transcript of the presentations. The stoneware level is the next one. That's for $20 a month. You get all the previous benefits, plus you get one of our Potter's Roundtable t-shirts that looks like this. And the final level that we have is what we're calling the porcelain patron level, which is for $50 a month. And again, you get all the previous benefits. You also get a handmade by Dennis, one of our founding members here, a handmade Potter's Roundtable mug. The next topic in the series will be safety in the pottery studio. Thank you for visiting with us today.
The Potter's Roundtable is brought to you by Washington Street Studios and our patrons. If you enjoy the show, please subscribe, give us a 5-star review, and tell your friends. If you want to learn more about Washington Street Studios and shared studio memberships, please visit our website at www.hfclay.com. Thank you, and we'll see you again next time on the Potter's Roundtable.